What we're going to do today is we're going to talk about how to find confidence intervals for means instead of proportions. Does that idea make sense? So proportion, that's always a percentage, a p-hat kind of thing, right? This is for means, like what is the average body temperature of a person? What is the average height of somebody in this class? That's no longer a number between 0 and 1. Does that make sense? Okay. So, it's a little review thing. Remember that this confidence level tells us the percentage of intervals computed using the same procedure that are actually going to contain the true value. Because if you do this like procedure repeatedly for lots of samples, most of them equal to confidence level will cover the actual thing you're looking for. So a higher confidence level means you've got a higher chance you're going to cover a larger proportion of your intervals are going to cover the real thing. And in the previous chapter, we found estimates of proportions, but in this chapter, we're going to find estimates of mean values. So what is the thing that is a fixed population characteristic and can't be determined because we cannot measure all units? What's that thing called? A parameter. Good. Or a population parameter. And we're going to use a statistic or an estimate from a sample to estimate this parameter. What is the really general format for a confidence interval? You've got your sample statistic, which I'll call my sample stat, plus minus some multiplier, times the standard error of your sample stat. For the previous lesson, we had two kinds of sample stats. They were either p-hat, in chapter 10, like one proportion, right? The other one you did, which was on Friday, you did p1 hat minus p2, which is the difference in proportions, right? Today, our sample statistic is going to be x bar. So we'll have things that are going to be like x bar plus or minus some multiplier times the standard error of x bar. So all that changed is the thing that is your sample statistic. And in the previous chapter, where did you find your multipliers? I either gave you told you what they were, right? But they came from that Z table, didn't they? We actually found some weird ones ourselves using the Z table. Today, the multipliers we're going to use are going to come from these T table things. And what the multiplier is depends on how large your sample size is. And when you pick bigger sample sizes, as in really even over 30, this multiplier is close to the Z values we use. It's just you have bigger multipliers, i.e. less accuracy for small samples. That's what this happens here. Okay, so things like estimating the mean of a quantitative variable, your general format of a confidence interval for this thing is going to be x bar plus or minus your multiplier times the standard error of x bar. And things you might care about, for example, what is the mean number of hours TV watched per day by, 12-year-olds. You could take a sample, you could ask, these kids or kids' parents, how much TV do they watch, and then you could find a confidence interval for how much TV is watched. Be the mean of one group. Were paired differences in essence different than regular means? Remember the paired difference example is kind of like taking someone's before weight and someone's after weight in a diet study, or mothers and daughters, difference in heights. Those are also an obvious pair, right? So when you're talking about paired differences, you always have a pair of things, before, after, mother, daughter, father, son, and you find the difference, and then you average those differences. So the notation here was D bar plus or minus some multiplier times the standard error of D bar. And the implied first step is you find the differences and then you average them. This is that order. So, for example, the mean before minus after on a weight loss program. On the last day of notes for this week, I took the abstract of a study done by Stanford that compared 4 diet programs, and they have confidence intervals in their abstract. So we'll just talk about what they mean. Like, that's a real thing. Like, I found it I read about it in a book, found the abstract on the internet, put that in your notes. It's kind of fun. Okay. And then the difference in 2 population means for a quantitative variable. So because we actually have 2 separate things, that's where we have this, our x1 bar minus x2 bar will be our sample statistic, plus or minus that multiplier, oh, I just missed my L, times the standard error of x1 bar minus x2 bar. Oh.
And that formula would look the same as we did for p-hat 1 minus p-hat 2?
It would look very similar, except for the formula for this standard error is a little bit different, because there's no proportion.
Right.
So that was the one, we did it in chapter 9, so I think we'll remember it when we come back to it. I think that we don't get there till Friday. But it was root sigma 1 squared over n1 plus sigma 2 squared over n2.
Yeah.
Yeah. Yep. So things you might want to compare there is something to the effects of like average height, GHT, men versus women. And if we're just looking at men versus women and not like husbands and wives, there's no obvious pairing going on there. I could take this class and say I can average all the heights of the guys, all the heights of the women, and then we'll see how different those things are. But 2 separate groups. And this section mostly is just review. So one thing we talked a lot about in chapter 9 is how can you distinguish these paired things versus these 2 separate samples. So paired data means that the data have been observed in natural pairs. So one example, same measurement taken twice. So what's my example for that every single time? Diet before and after, okay, something like that. And we could also be not measuring weight loss, we could be measuring like blood pressure, right? We could be comparing other things other than just how much weight you lost. Blood pressure, HDL, LDL, stuff like that. Similar individuals are paired before giving the treatment in an experiment, and each member of a pair then receives different treatment. So there was an example where we paired based on age. Does that ring a bell? There was a problem that said, okay, well, you have these people between the ages of 40 and 65, and we want to test these 2 different memorization techniques, and how old somebody is going to affect how well they can memorize stuff. And so you paired people with people that were the similar age to each other, and then you compared the techniques. Okay, 2 different variables measured for each individual, and there is an interest in the amount of difference between the 2 variables. I don't know, maybe some kind of height-weight comparison or some foot size, hand size comparison, but somehow, or HDL and LDL, you could compare how different these 2 things are. Cholesterol, but you have 2 measurements for a single person. So independent samples, when measurements are not, when one sample are not related to the other. So you take random samples from 2 populations and the same response variable is recorded for each individual. So I could compare like class at UAF to class at UAA, your 2 separate groups for the most part. You take 1 random sample and a variable is recorded for each of you, but then I categorize you based on you belong to one population or another. So I'll say, okay, I got my class, then I'm going to divide you along gender lines into 2 groups. Or I could divide you by class lines, right? I could say everybody's under 1st year, 2nd year, 3rd year, higher. Or participants are assigned to one of 2 treatment conditions, diet or exercise. This could also be like a drug versus a placebo. Okay, so in that, tell me whether it's more appropriate to use a procedure for paired data or 2 independent samples to estimate the difference of interest. So a researcher wants to estimate the difference between the mean scores on a memorization test for people over 60 and people under 40. So is that paired or 2 separate groups? That's two, and it's not like a mother and their kids, right? It's just two separate groups. So 2 independent samples. Because there are two groups. And the notation for that would be mu1 minus mu2. Women give their actual and desired weights in a survey. Is there a natural pairing for someone's actual and desired weight? Yes, like one person's, right? So this would be paired data. Two treatments for reducing cholesterol are compared. 40 people with high cholesterol use the first treatment, and 40 other people with high cholesterol use the second. An estimate of the difference between the mean decrease in cholesterol for treatment 1 and the mean decrease in cholesterol for treatment 2 is desired. Okay, so are they two groups of people or are they paired somehow? Okay, well, there's 40 people in each group, right? So it would be possible to pair them, but did they say they did that? No, they just, the 40, in the first group, they just got the first treatment. Second group, they got the second treatment. So, in that case, there is no pairing. This is two independent samples. So, could you guys imagine a way to make part C paired? So what you could do is you could take your 80 people and you could match them what their cholesterol was in the beginning. Does that make sense? Then you could give them the treatment and see how it went. But they didn't say they did that. They just said that they had people and they divided them into two even groups and they gave one this drug, one that drug. So, no pairing. Okay, so the standard error of the sample statistic is the estimated standard deviation of the sampling distribution. So, does anybody remember what the SE of X bar is? What was the standard deviation of X bar? Do you remember that? This was sigma over root n. Does that ring a bell? So when you find the standard error, you don't actually know what the sigma is, right? So you estimate that with S, the sample standard deviation. This is S over root n, where S is equal to the sample standard deviation. Okay, how about for D bar? Is D bar any different, really? Nah, it's still S over root n, and S is, and we'll say S sub D. That's how they say that it came from a differences thing.
So to find S, we use that top formula code.
To find S, you're usually given it because it's so icky, but we found S in chapter 2. That was this thing that did the sum xi minus x bar squared over n minus 1. Does that ring a bell from a long time ago? I know it's a very long time ago, but this was in chapter 2. I cannot remember which day. If you want to reference your notes, so that's where it was.
There were 14 birds. What now?
There were 2 days of that lesson, I know, because it was like the first week of class. But the thing is because this was like involved doing like sample data minus your mean squared for every single number you had, right? Dividing by n minus 1, and then square rooting. It was tedious. You had one your first test. But usually the problem will tell you what that is because it's so tedious to calculate. Does that make sense? They'll say the sample standard deviation is this number, just run with it. Okay, there will be a couple problems where I ask you to find it, but we'll also review that before you have that homework assignment because I realized that September was a long time ago and we all forgot. Yes? Okay. Alrighty. So in a class survey conducted at Penn State, 175 students were asked how many hours they studied in a typical day. Pretend that I know how to put spaces and stuff. The mean from this sample was 2.09 hours with a standard deviation of 1.644. So calculate the standard error of the mean. So what is x bar?
2.09.
And did this problem tell us the sample standard deviation? Yeah. 1.644, right? Okay. So we want to find the standard error of x bar, which is s over root n. Oh, and what was our n? 175, great. So what goes in for s? 1.644 over root 175. And that comes out to be about, I got 0.124. Okay. Yay. So that tells you if you do 100, if you repeatedly do samples of 175 and you find the average number of hours studied per day, that you can expect this kind of variation. That's about your standard deviation.
I got 0.125.
0.12, what came next?
Oh, 1245.
Well, did you get that? What'd you get?
Well, I erased it from my calculator.
Oh, okay.
Certainly do it again quickly.
1242.
Yeah, 0.1242.
Something happened, I don't know what, okay? Maybe, I did it where I put in like 664 instead of 644. It's not that big of a deal. You made some kind of silly little mistake. Okay. This is the standard error for the difference in two sample means. That's what you were asking about. So the formula that we had in chapter 9, instead of s's, there were sigmas. It was sigma 1 squared plus over n1, sigma 2 squared over n2. So, okay. In each part, use the information given to calculate the appropriate standard error. So this is paired differences. We're given a single n and the sample standard deviation. So what we're looking for here is the standard error of d bar, which is SD over root n. This one's kind of nice, it works out pretty. What goes in for SD? Over root of, which works out to be 21 over 7, which is 3. It's kind of a large standard deviation, right? Yeah. Okay, how about this next one? So I have a difference in means for two independent samples. So there I want the standard error. If it's two independent samples, what's my sample statistic? Is it x bar, d bar, or x1 bar minus x2 bar? But two independent samples. So two samples means you have two means. So x1 bar minus x2 bar. So that formula is s1 squared over n1 plus s2 squared over n2. Does the do the n1s and n2s have to be the same? No. Do the s's have to be the same? No, they are in this case, but that's just, special. So we'll have 10 squared over 50 plus 10 squared over 50. This works out nice as well. What's 10 squared divided by 50 makes 2. So I got 2 plus 2, which becomes root 4, which equals 2. But the thing to think is if you have independent samples and you're given two sample sizes, that's this guy. See what I'm saying? Okay. All right, one more, then we'll talk about those t-tables quick and give you a quiz. Suppose that a random sample of 64 men has a mean foot length of 27.5 centimeters, and the standard deviation of that sample is 2. So is this S or is it sigma? It's S because it came from a sample. Okay. Calculate the standard error of this sample mean. So the standard error of x bar is just S over root n, which is 2 over root 64, which is 8. And I think 2 over 8 reduces to 0.25, right? Okay. So what this means is that the approximate standard deviation of x bar is 0.25 for samples of what size? 64. What happened to this standard deviation as your ends got bigger? It got smaller. Okay, so this is saying that if you have samples of 64, you're going to expect 68% of the samples to fall within, plus or minus that 0.25. Right, 95 between plus or minus twice that much, approximately. Right, that's that whole approximate thing. But the kicker is it's an estimate of the standard deviation of x bar, which tells you how much x bar varies. Okay, last thing on today's lesson is how to find that multiplier. So this multiplier thing is the main difference between the previous stuff and the stuff we're going to do now. So this table, the side you're going to use is the front side. Okay, so for blank, you use the z distribution. So for proportions, you use a z distribution, which is that whole z table. And for parameters involving means, you're going to use the t distribution. So it's z for proportions and t's for means. And with this stuff, so with the means stuff, there is one more parameter called the degrees of freedom, and that's abbreviated DF. And for problems involving a single mean or a mean of paired differences, this is n minus 1, or that's your sample size. And using this picture on that table is still like, bell-shaped, symmetric, stuff like that. The difference is that the tails are supposed to be a little bit fatter. And so for a confidence interval for a population mean, the t-star multiplier is the value in a t-distribution such that the area between negative t-star and positive t-star is the confidence level you want. So let's use this table to actually find that multiplier for a few things. Okay, so if we have 15 degrees of freedom, and a 95% confidence level. So I think I might have made a mistake in my notes, we'll see if this is right, but if your degrees of freedom was 15, what was your sample size? 16. Okay, so on this table, you see how in the left column there's DF for degrees of freedom, and as you go over is the confidence level. So look at 15, and go over until you see 95% confidence, and that's your multiplier, 2.13. So T star is 2.13. We're on the T table thing. So degrees of freedom 15 over to the confidence level of 0.95. Okay. Next one, DF equals 30 means your sample size was n equals 31. Okay, so go down to 30 and over to 95% confidence, and what is your 90% confidence, sorry, what is your multiplier? 1.70. Let me finish now, I think I can answer your question. And then the last one, your n was actually, this is n equals 10. So what is the degrees of freedom for this guy? 9. Okay, so I'll go down to DF equals 9, and then over to 95% confidence level. Your T star is 2.26. So my notes are correct. If it happens, okay, just FYI, one more thing, and then you can do your quiz. If I had given you n equaled 32, let's say, what would your DF be?
31.
Is that on your table? No, just pick the closest one. Does that make sense? Just pick 30. Because you can use software to get it exactly, but you see how once you go bigger than like 30, the numbers get kind of close together? You know, see as the n gets big, that goes to 1.96 for 95% confidence, which is like your z thing. So, there you go.